All right. So, the question is about a pop fly versus a line drive. So that's what we're going to try to do. This is a pop fly. Okay, that's a pop fly. That takes a while. What about a line drive? Not quite as long, but now you know the difference. So let's see how that goes. Good morning. Oh wait, no, it's good afternoon now. I have a question for you. Why would anybody in their right mind just divide sine by tangent? It's a silly thing to do, honestly. So maybe I can figure out why. I know that sine is opposite over hypotenuse divided by tangent, which is opposite over adjacent. And that's a compound fraction, which, ugh. So instead of doing that, instead of dividing by a fraction, I will multiply by, the reciprocal, which is adjacent over opposite. And hopefully you notice the thing. The thing is, when these cancel, look what's left. Adjacent over hypotenuse, which leads me back to my original question. Why on earth would you simply divide sine by tangent? Well, just cause. That's right. Ow. Wasn't that bad. Okay. Anyway. We have a baseball problem. And we have an equation that will help us figure out the best launch angle for hitting a home run over a given distance fence. All right, so here's what we know. I'll bring this up to you, and you can read it, and it says, a baseball leaves a bat with an initial speed of 30 meters per second. And clears a fence 90.5 meters away. The height of the fence is the same height as the initial height of the batted ball. That's a really short fence, by the way. If the distance of the ball traveled is given by d, the distance, equal to v sub 0 squared times sine of 2 theta, where 9.8 is in meters per second squared. Why 9.8? Physics students? Why 9.8 meters per second squared? Oh yes, that's gravity, pulling the ball down. Find the interval of possible launch angles of the ball, which means somewhere between a pop fly that's too high and a line drive that's too low. Somewhere in between. So, here we go. What's given to me? Well, to start, the speed of the ball is given to me. So I can replace v sub 0 with something I know, 30 meters per second. There is something else I know. It's what? The distance, which is 90.5 meters. Cool. Now, if only I could get to that theta. It's buried amongst all that junk surrounding it. Well, it's not too bad. The thing I should do is I have my sine of 2 theta multiplied by 30 squared and divided by 9.8. Brace yourself. We're going to do 2 steps in 1. Technically, it's 3 steps. So Instead of doing multiplication by a thing and division by a thing, I'm going to multiply by the divided thing and divide by the multiplied thing. What's that multiplied thing worth? 30 squared? Oh yes, 900. I'm going to do the same thing to both sides. 9.8 over 900. And what's going to happen? Well, they're going to cancel. The 9.8s are going to cancel. And in my equivalent equation to follow, I have sine of 2 theta and I'm going to go ahead and multiply those top two things and call it 886.9 and keep the over 900. Just keep it like that. Okay? You go any further than that and the decimal gets okay. I want to get to this theta. There's a 2 in the way and a sign. I gotta get rid of the sign first. So I'm going to hit this thing with a lot of hitting going on. Inverse sine, aka arc sine. I'm going to hit both sides with that. After all, this is a baseball problem. There should be a lot of hitting. If there's not, it's a boring game. Okay, so inverse sine knocks out the sine. Is that kind of like the third base coach going, wiping off the sine? No. So what's left is 2 theta equals. Now, before you use arc sine, what do you need to remember? Oh yes. Is this a physical angle or is it a cyclical activity? It's a physical angle, which means you need to make sure that your graphing utility, whether you're a Desmos or a graphing calculator or whatever, needs to be set to degrees. So let's take a look at that. And I will do inverse sine of 886.9 divided by 900. And it gives me 80.2 degrees. Very good. Not something you can figure out with your little coordinate plane and your special triangles. So 80.2 degrees. Okay. Now that's one possibility. That's either the line drive or the pop fly. Kind of feels like the pop fly at 80 degrees, doesn't it? Hold on. How would I get the other angle? Well, I would take this and subtract it from 180 degrees. So 180 degrees minus 80.2 is 99.8 degrees. Wow, they're both large angles. Oh, of course they are, because that's 2 theta. Yes. So, what has to happen next? I have to divide everybody by 2. And I find out on this side 40.1 degrees. This is now theta, and this becomes 49.9 degrees. So as long as theta is between 40.1 and 49.9 degrees, that ball is going over the fence. Yeah. Okay, this is for you baseball people. So here's your equation that you were working on up here. And here's what happens when you take the speed and increase it to pretty much like the lowest speed you can actually do and still be able to have a baseball game. 20 meters per second. It's about 44 miles per hour, pretty slow. This is the hit angle. It won't let me use theta. So I can bring that angle up, and you can see that at 20 meters per second, nobody's hitting a 90.5 meter fence, no matter what angle you do. But if you increase the power to 29 meters per second, I still, no matter what angle I get, I cannot reach the fence. So what happens if I go to 50? 50 meters per second happens to be about what the strongest Major League Baseball players can hit. And you can see that, anywhere from, if that blue line is the fence, then they easily hit it, even if they just do a 10-degree angle line drive or about an 80-degree angle pop fly. They will put it outside of a high school fence. So let's bring it back to realistic high school speeds, which is 30 meters per second. Okay, and you can see there's this little tiny zone right about here where it's reasonable to put a ball over the fence. So anything over here, the angle's too low, it's too much of a line drive, it's not going over the fence. Anything on this side is too much of a pop fly, the angle's too steep. This would be straight up 90 degrees, land on your head. So I want to get inside of this zone right here. So anywhere from about 40 degrees, we calculated 40.1, and then all the way over here to about 50 degrees, where we calculated 49.9. That little zone in there is the balance between pop fly and line drive that puts a ball over a fence with roughly high school speeds and high school distances. Yes.